Okay, I hope you can hear me. Okay, let's start. Yes, thank you very much. Good evening, everyone in Singapore, Kuala Lumpur, Jakarta, or other East Asia and Pacific countries, and good morning for everyone in the West area, part of the world. Welcome to our first meetup for our quantum computing Qsharp developers community in Singapore. So yeah, before we started, I just want to say many thanks for everyone who viewed this live stream, and I hope we all can learn together. Uh, because this is also the we supposed to do this in March, but due to COVID situation, we unable to do this in March in person session. So I have to do this live stream for the first time. Uh, I promise after this COVID situation, we'll be able to have some in-person meetup, and we'll be able to chit chat with and socialize. As usual. I miss that part. I miss that. I miss that time. Okay. So before I start, I just want to give a disclaimer that I am not a physicist nor even a quantum mechanics expert. Please level with me. I'm just a software developer that uses software technologies for solving problems. Most of us is doing this. So any deep mathematical or details of quantum mechanics, I probably won't be able to answer it, and hopefully someone in the community can help me to answer that. Hopefully by chatting. Good evening from Perth, Australia. Hi there. Yeah. Hello, mate. Yes. Thanks for joining. And yeah, and of course, however, I'm willing to learn quantum computing because software programming is one of my hobbies, and this quantum thing is awesome. I love it. You probably love it too after joining this session. Okay, let's start. The agenda for this my speaking is first we want to talk a brief of classical computing fundamental unit, just to remind us what what technology that we are using currently in terms of using uh, computation for technology for computation. That's the fundamental unit that we need to know. And then after that, we're going to talk about the quantum computing fundamental unit, and we can see the difference and how we compare that. And then we are going to share. I am going to share what quantum computing can do for us, and why we need to learn quantum computing as of now. Even, I just want to remind you, there is no quantum computer right now. They're still under development, under research, still not stable, but they're maybe within, I don't know, 5-10 years. Closely, they will get this. Hopefully, sooner. Okay. And then I'm going to share with you the tools for developing software for quantum computing using Microsoft Quantum Development Kit. And you probably already know that we also can use Jupyter, Qsharp, using Jupyter. Later, I'm going to share with you how to spin the Docker container, and then basically just click a button. Okay. Okay, and then of course demo of some of the Q sharp, but because this one is introduction and it's a first meetup, I won't talk in details about the coding itself. It's just a demo, and then the next meetup maybe we can talk more deeply and we create real software application using quantum Q sharp. Okay. Okay, let's talk about the classical computing fundamental unit. We all know this. Uh, as you can see this even in the image here, you can see this electronics, a lot of things. And we probably heard the term analog and digital electronics, although they are all of the same electronics kind of stuff, but the way the signal is processed is kind of different. But we're not going to talk about analog now. We're going to talk about digital electronics in the classical computing fundamental unit. And here's an example. Yes, it's an amplifier, but this is a digital amplifier, not the analog one. Of course, the input probably analog, but currently most amplifier has a maybe some kind of like a, to make the sound cleaner, to make a beautiful sound effect. They fit the analog into the digital, and then they process it using a digital uh, computational inside the device. And of course, probably this one is solid state device, a solid state drive, and then of course mobile phone, and then of course laptop. So these are all the classical computing devices. So what are in commons of these all of them is actually they are all in common in one thing, that is a transistors. So all of these devices are all using transistors. As you can see, the transistor has a lot of types and models, but we all the function of the transistor are all the same. Some of us probably asking, what is the function of transistor? Okay, I'm just probably going to remind you. Maybe you already know about this. There is some, for example, there's a NPN transistor here, is a negative, positive, negative, and PNP, which is positive, negative, positive. So, what is transistor? So, transistor is actually a semiconductor component. Is an element which is acts like a switch. So, it's a simple semiconductor element that they bond together, and then they some kind of like electronic component that can block some of the current, and then they can release some of the current by giving some voltage in one of the pin. Maybe I can give you an example later. So this is a switch. It's a simple switch. It's like, for example, if you use your finger here to switch on and off in here, that one you need your finger. It's like a kind of like a mechanic, right? It's a mechanical switch. But in transistor, you can do the same by actually by feeding this base. This is base collector emitter, and by feeding with a certain current voltage, so the current from this side can flow. So for example, if I pass a current in here with a certain voltage, let's say 5 volt, for example, this they cannot go. They cannot go. So how to make this thing open? We give a current in here. There's certain specification of every transistor. Some of them require a certain voltage and the threshold. And once you give it to this base pin, and the current will be flowing here. So that is how we do switching instead of mechanical like this. We do it electronically by feeding a current to open and close the switch gate. So that is actually that's all. That's classical computer in that sense. Okay. It's just, yeah, like this. So if I can play around with this, it's on, off. Yeah, see, that's it's nothing more than you can see in here. But that is, we call it a state. When we turn it off, the state is off. When we turn it on, the state is on. So if you can see, this is, you only have one state. If it is off, it's not on. If it is on, it's not off. Okay, so it's only one state. You cannot do anything. It's like you look at a coin on the top. You cannot see the bottom unless you flip the coin, and you will see the other side, but you cannot see the other side. So that is one state, the meaning of one state. So this state is if we translate this state in the classical computing, we call it binary. Bi meaning my meaning is two, and then is a number. So it is, we call it a bit. Okay, so if it is off, is a bit, state of bit off and state of bit on. And in the numerical, usually they use it a 0 and 1 to distinguish between these two states. So if you want to turn it off, the number is 0. If you turn it on, the number is 1. So this is how they play around with this binary concept. Okay. And then if we look at this, maybe I just want to share with you. Maybe some of you have remember this electronic schematic diagram. If you play around with electronics when you're a kid, I did actually. So I love this kind of my first electronic device that I play around, my electronics circuit diagram that I play around. So this is a flip-flop actually. So if you can see, this is the battery 9 volt, and there's a switch in here. As you can see, this is the current is blocked; they cannot go anywhere. But when you switch on, they try to send the flow. The current is flowing, and they try to it's a circuit. So what happened is in here when the current is passing, this is a capacitor, 100 microfarad. So what happened is they will charge this. The capacitor behavior is they will charge and discharge in a certain threshold. So when it's discharged, they will go to the base and ignite this. So what happened? This gate will open. Boom. When the gate is open, this LED will turn on. Will on, and this LED will off. Why? Because this one is blocked. On the same time, once this thing is charged, the gate is open, it's charging this one. While this one is already discharged, this one is charging, and then once it's full, they will discharge. And because in the base, if you give a current on the base, this gate will open and this LED will be on. And because this one is already discharged and this one is already closed, this will be off. So what happened is like flip flop like this. If you play around, you're gonna love it. It's just like this. So the timer, the time that they do flip flop in here, it depends on the capacitor that you play around in here. You can make it higher, you make it smaller, the number of capacitor, and you can see that this flip flop can be more faster or can be slower. So that's the idea of one state. You cannot do anything if you flip one, you only get one. Okay, and how to make this work in the classical computer. So what they do is they squeeze all these transistor into a chip as much as they can, and they make it for computational like this. The data that they represent for the binary, it's we call it the binary representation. So how do they put the data, for example, to send a data inside this classical computer? What they do is doing like this. So this is a 2 to the power of 0 to the power of 1 and so forth until to the power of n. So this is the way the binary representation works. Just imagine this one is coming from a certain digit of transistor, the output, and then if they send a 5 volt in here, if it is 1 is 5 volt, if it is 0 is 0, and so forth. I give an example, simple example. If you look at this, for example, it's a 8 bits data. This is 1. Consider this as 5 volt, 5 volt, 5 volt, 0, 5 volt, 5 volt, 0, 5 volt. Is just like that. So you can, as you can see inside this chip, they are very busy. Currently, like for example, a processor can squeeze up to billion of transistors inside. You just imagine this what will happen. And then they can calculate like this by adding the one that has 5 volt, which is 1. The state is 1, and then we can calculate. Oh, the data is 183 for 1 1 1 1 1 1 1 1 0 1 1 0 1. That's how they do it in the classical computers. Uh, and this, as you can see, this is become an issue, right? The more you need more numbers, for example, this thing must add more as well. Okay, so yeah, we try to make things like, for example, like 32-bit, 64 bits computer, but still not enough. Because why? Maybe I just want to remind us, we remember the limitations that Moore's law is one of the founder of Intel. They say that the Moore's law states that the number of transistors on a microchip doubles about every 2 years, though the cost of the computers is half, which is true, yeah, except probably a certain product. Maybe you know what I'm talking about. I may be using in one of them, still expensive. I don't know why. It's supposed to be cheaper, but that's reality. Someone gets to make money lah. And then while doing this, they squeeze the transistor. Uh, this thing becomes a Moore's law. The more we squeeze the transistor, every 2 years is getting smaller, smaller, smaller. How small can we get? That's the question, right? How small can we get? And the Moore's law also says the growth of the microprocessor is exponential. As you can see, this is a logarithmic. Exponential is meaning that sometime, somewhere, someday, it will be impossible to squeeze anymore. And it's true. It raised the big questions. We know the big question is how small and dense the physical limits of a transistor can be inside a microprocessor chip. I give you a simple photo here as an example. The answer is actually Morse itself. Answer it. Cannot continue forever. So we cannot continue to squeeze this transistor. Is enough is when it's enough is enough. We cannot make it smaller anymore. And some of us may be thinking like, okay, why don't we just do parallel computing? Okay, the answer is yes, we can do that. But later we shall see there's a limitation on that thing. There's a limitation in terms of the computational, not the device itself. So the limitation is not only in the device, but also in terms of the computational performance. That is why we want to learn quantum computing. Okay, so the next step, we are going to talk about the quantum computing fundamental unit. Just now, we already talked about the binary, the bits, which is one state. After we recall the classical computing fundamental unit, let's now see how quantum computing represents its fundamental unit. Uh, I think from this part, we can then compare the difference and see why quantum computing is so important for solving lots of problems in the world. That is one of my messages for the community here in Singapore, to learn quantum computing, especially the language first, at least before we have the real machine in our hand, hopefully. But once we already know that, then that means we already know how to do quantum computing. Okay. Okay. So in quantum computing, they call it qubit instead of bit. Qubit is a quantum bit, so it's still a bit, but it's quantum bit. It's a little bit different. So unlike classical computing bit, qubit has a basic unit of quantum information. Similar, actually, I have to say, similar like the binary, like bit. But the version of the behavior of this bit is totally different with the binary, because in qubit it has two states, not only one. This is the first time when I got my head spinning. Like, later you see. Let's see whether you're spinning or not. So in the this qubit is a two state. and displaying a strange thing that we cannot. If we say the logic doesn't make sense, right? But according to the scientists, yes, it's really work, and it is, and that's why the quantum mechanics is the quantum computing is actually they try to make it, and because they can prove it. Okay, so while the classical computer binary must only have one state of 0 or 1, the qubit can have two states. It can be 0, it can be 1, and can be both 0 and 1. Okay, okay, I know I also spinning my head also spinning last time when I try to understand this, how this thing can be 0 and 1 at the same time. Okay, but as a software developer, I don't want to go deep into that. Let the physicists and quantum expert do their job. I believe they will be able to make it simple, but we need to accept that it is exists and it is like that. So the quantum computing is using qubit instead of bit. Okay. So how do we represent this qubit? It's simple. So this is zero, for example, and this is one, and also can be like this. Ah, there's two states. So this is the first state, 0 or 1, and the other one is 0, 0 and 1. Yeah, like that. Okay. So because of this peculiar things in quantum physics, qubit can be one of these three states. Uh, how should I explain this? Put it like this, lah. If you're a software developer, just don't think about it. Just believe that this thing exists. I try to understand, but how? But it exists. However, actually can be proved in the mathematics side. Okay, once you understand the representation. So what they are talking about is actually the representation of this. This is one. This is the qubit, the state. So the way they represent is actually by using a vector here, a vector basis. Is they call it the orthonormal, and then this is if it is the state is one, so that is how they represent. So this is one qubit. Okay, this two is one qubit has two state, which you this one can be all together. So but we also can combine this the same like binary. For example, I give you an example. For example, we want to combine these two like this. So this is become 4. Okay, 0 0. So this like this. So this is actually 2 qubit. And as you can see in journal, the n qubits are represented by superposition state vector over 2 to the power of n dimensional Hilbert space. I don't know who's the guy is, but everywhere I read the book, everywhere his name is on the quantum mechanics thing. Yeah, just yeah, for me I just accept this. But the way they represent this, actually this is how we will do the coding. If we want to do some kind of like logic, for example, uh, uh, maybe next meetup I can explain how to calculate this easily. Actually very easy. In some sense it actually makes sense that a qubit can be 0 state, 1, or 0 and 1. It actually makes sense. And again, just want to reiterate for the non-quantum physics like me. How do we imagine this? Why do we have to learn this quantum computing things? Okay, so I learned this from Chuck Bates. His video. For example, like this. This is how we're doing the simulation traversing maze. In classical computing, as you can see in here, when we try to solve this, it's like we are a kid, you know. We try this, and then oh no, cannot. We try again, and then oh it's red. Okay, we cannot. And then what happened is we go around. We try to solve it. Oh, this one is stuck, and then we try again. Supposedly we can go back, but sometimes computer when it's stuck, they just go start all over again. So this is what happened. So this is what you will get by using classical computing. It is a multiple try repetition and optimization. For example, like this, when they find out this one, it can be like this one, right? So, but when they try to after simulating to find the nearest, the way out, not the nearest, I mean the way out, then they will optimize. Maybe they find, okay, this is the optimized one. So this is the way the classical computing calculate how to solve this maze or traversing maze graph. Uh, Maybe I can say graph. So how do quantum computing solve this? If it is like this, multiple try repetition, optimization. As you can see, this is all of the way they move. Okay, but the classical computing cannot, for example, flip this one into one or flip this into zero or one. So what happened is if it is cannot go here, then cannot go here. In quantum computing, to solve this, they just do like this. There, one shot, and they find a way out and find the shortest, the optimized one, and it's yeah, just like that. So this is how they solve the maze by doing like this. They don't care about this because they can just flip. They can just superposition to from a certain 0 1 or 0 0 1. So yeah, of course, it's cheating, but hey, it's quantum. They can do it. The qubit can do that. So it's good for us for this one. But then probably you were thinking that parallel computing also can do this. I also think like that before. But the thing is, what happened if the complexities of the problem is is not like this? It can be 100 times, 1,000 times, a billion times more complex. Just imagine that if it is like this, but a billion more complex than this one. How many times the classical computing will do to find the way out, for example, or to solve the problem, to simulate this? Because this thing kind of thing you cannot use AI. Okay, in maze, you can use AI if the maze never change. But if the maze is random and always change, the AI don't have the history. Bye bye to that. Okay, so AI won't work with this. So you have to use simulation. So simulation is the essential to solve this kind of thing by brute force trying all way to solve this maze. So this is quantum computing come to the picture to solve this kind of thing. This is one of the example. And then how do we scale this? I give the example for scaling lah. Let's say this one is a classical computer. You have 2 bits. Okay, you know this 2 bits. Yeah, it's 2 bits. So you cannot do more than three, right? This one is 0 0. This one is 3. So that is the maximum value that you can do in here. Okay, so now what happened, for example, in terms of the scaling, suppose the we want to increase this into 4 bit, for example, into 4 bit. How do we represent this in scaling for this? You can. So what you have to do, if we want to have this 2 state available in all states, okay, so we can, is this is 2, right? Because this one 2 and this number is 3, you can maximum is 3, is 2 to the power 3. You need to make it 8. Okay, so you have to make it 8 to be able to have all state, the 3 state. You cannot do it by one, by 2 bits in classical computing. That's the problem. So by this 2 8, then you be able to solve this 2 bit issue using classical computing. Uh, but this kind of thing actually can be solved by using 2 qubits only. It is pretty simple. It's 2 qubit to solve this. So we don't have to have 8 bits. Just 2 qubit to solve this 8-bit situation. And all of this the 2 bits, all of the state be able to the 4 state we be able to get the output. Okay. And then the second question is, what happen if we want to scale again? Like for example, we double it again into like combining the switch to get more bits. Let's say like this one, 64 bits. But in qubit, we only need 4. You get it now? I go back, this 2, you only need 2 qubit. And then for 64, you will see this 4 qubit. Okay? Remember, to the power of n, which n is the number of the qubits. So what happened? For example, let's say I want 300 qubits. How many classical computer I need to match these 300 qubits? Remember, 1 qubit can solve can have 4 in classical computer. So what happened is, for this 300 qubit, you can get 2 million to the trillion, 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 trillion of classical computer bits. Okay, so no need to count. It's 90 zeros here. You see how crazy it is? Quantum computing. So by just using 300 qubits, we be able to have this kind of powerful classical computing, which is impossible. How do we get this? How many? Even if we join the entire PCs in the world since 1980s, if you have until now, we still cannot get this. This is too much, for example. But in quantum computing, you'll be able to do this. Okay, so that is why I want to learn quantum computing, because this is crazy. You just Yeah, of course, for small, of course we can use parallel computing. Yes, go ahead. 64-bit. Yes. So this is your PC, 64-bit. Yes. It's 4 qubit in real, real quantum computers, but still not exist. If we exist, then we love it. Okay. And 300 qubits is like this. Okay. So the why we have to have this such powerful machine. Okay. So actually, we want to use this for what the quantum computing can do for us. Yeah. So for the most important, because I'm working in a simulation environment, which is I'm working in the central a center of excellence for next generation terminal ports and logistics, which is AI is out of questions. Maybe it's number two, AI. We cannot use AI. Everything must use simulation because there is no history. They can fit. We can simulate to fit the AI. That one we can. So we simulate the optimized one. We fit to the AI. So the AI be able to use this history to solve certain issue after they get the real input from simulation. The good thing about simulation is the right one. AI is prediction. Simulation is probability, but is an optimized one, and it's always right one. So it's not prediction. It's definitely is the correct one, because when you run simulation, it is following the flow that exactly what the simulation has to do. Okay. Uh, Number two, cybersecurity. For example, if you hear the news that quantum computers exist tomorrow, Maybe you need to be careful with your bank account and certificate. No, I'm just joking. Yeah. So quantum computing can crack any certificate, the current certificate, the private key certificate, using prime number in just probably less than seconds. Yes, they just can crack everything because the private key usually is two numbers, prime numbers times prime numbers, and then you get the public key. They give it to public key, and then how to reverse back, that is almost impossible to get that. Okay, so this is one of the usage of quantum computing, but no need to worry. They already have some algorithm to replace this certificate key pair kind of thing with the more powerful one. So quantum algorithm with the quantum security. Maybe they will name it quantum certificate. I don't know, or quantum security. I don't know. But currently, if you have a Bitcoin, for example, and you heard that quantum computing exists, maybe you need to cash out. I'm just joking. And also financial. For example, if you want to do investment, usually you do simulation and you try to find the best option. But if it is small data, yes, if your bank account is small, it's like where I want to invest. But if you have a lot of portfolios worldwide and you have a lot of huge big data you want to fit in into from the news in the world, if using classical computing, it feels like a random, but actually it's not random because someone's decide this or someone doing this. But using the financial simulation, it can try to find the best solution for your investment. Imagine that we all can be rich if you have the quantum computers in your hand. Okay, that is one of an example, hopefully. And then also for medicine, we know that virus, right? COVID. Hey, COVID, please screw you, go away, COVID. But it's happening. So this one also for medicine, sometimes when they do the what's to call it, the genome matching or this kind of thing, or for the pathogen, try to find a vaccine, it requires a high computational process by brute force simulation as well, trying this, trying that. Using classical computer can be like, is probably cannot find that easily. But maybe with quantum computing, they can do it. They can find a vaccine in just 1 hour, or maybe less than 1 hour to find the vaccine. How to create the link between this virus and the vaccine to remove what you call it, the RNA or something. I don't understand that one. So that is what happened in the real world that we can do in quantum computing. But for now, we don't have to bother about that because the quantum machine is still not here, but the quantum computing language is here. So there's something that we want to share, and we prepare. The good thing is when one if we use the quantum Qsharp, for example, language, we actually using this quantum simulator. So it's mimicking the real quantum machine, but it's using classical computer. Again, it's mimicking quantum computer using a classical computer. Therefore, the number of bits also limited because it's a 2 to the power of n. The more, even sometimes you add one more n because it's exponential, suddenly your PC is stop working. It's like stop working because they're doing computational very slow, and that's why there's a limit. So yeah, maybe I can do some demo first. I will show my demo here. So to install before the demo, I want to show to you. This is one of the example of the simulation. That is, if you go to the website, uh, learning solve optimization problem. this is a port, terminal port, how to optimize a container uh, for logistic, for example. So this is a way to use a quantum computer. Uh, they call it the quantum inspired optimization to solve the problem. So if you run this, we do this all the time in our research center. So yeah, this one is slow because we are using simulator, but this one is a video. But as you can see, the step here, they try to optimize this. Okay, so that is one thing, and a lot of express a lot of mathematics. Yeah, okay, and then how to install the QDK is actually by number one. If you have Visual Studio, you can use Microsoft Quantum Development Kit here. Okay, you can go to the marketplace and then search, or you can go directly from the extension of extension of Visual Studio. By the way, you also have this in uh, Visual Studio Code. If you don't want to use Visual Studio, you should be able to do this in Visual Studio Code. Okay. So no need to have a Visual Studio, but using Visual Studio Code also can. Okay, hold on. I am looking at some oh, it's not a question. Okay, thank you. Okay. Uh, hold on. I think I need to close my PowerPoint. I forgot to escape. Yeah, then this should fit. Let me just go to this and transition. Yep. Sorry about that. Okay, so this is the first one is the I'm going to try again because sorry just now I forgot to switch. So this is an example of how you solve these two terminal port logistics using simulation. It seems my hold on, it should be there. Oh yes, okay. Okay, so this is you can go to the learn, browse, and solve optimization problems by using quantum inspired optimization. And then for installing the QDK, you just go to this marketplace. Okay, and then I am going to show you how to spin uh, the Jupiter. So number one is we go to the GitHub slash Microsoft slash Quantum. All you have to do is just click this binder launch. Okay, binder, and this will spin up. You can see this is spinning the container, and then it should be there in 3, 2, 1. Okay. Yes, a little bit time here. Uh, yes, please. Spinning. It's like a quantum machine here. Okay, should be there. Okay, while we're waiting for this, let me just open my Visual Studio and show you how to get the extension here. You can get this by installing install this one, Quantum Microsoft Quantum Development Kit. Okay, And then the other one that is I can show it to you is via uh, beloved Visual Studio Code. And as you can see here in the extension, uh, there is a quantum development kit as well for Visual Studio Code. Okay, so if you don't want to use Visual Studio full, you can use Visual Studio Code to do quantum computing. By doing that, you can already start now. Let's see whether the binder is ready. Okay, it takes time, usually very fast. You might want to try this in your at your home. Is just now it's supposed to be faster. Maybe we switch to other browser. Usually that works. Let's try Chrome. Enable extension. No, remove. Okay, so this one is actually should be. I don't know why it's not working. So if it's a Jupyter, Jupyter notebook is yeah, you can just try this later. Okay. Okay, and then let's try coding. So we just open project for this, and then type Qsharp in here, and then you choose Qsharp application. There's a library, there's a test project, just Qsharp like that, and then you can name it in here, the project solution and project, and okay, and here is the Qsharp language. So it has a, this one is actually like using in C sharp, if you use C sharp, or import probably in some language. And then this one is the name of the namespace, and this is the entry point. Anything that has an entry point, it will be called first. This one is like a main in C sharp. So this is the hello quantum world. So if I just run this, it will run normally. Let's see this running. Okay, hold on. I think my here it is. It's showing on the other window, and you will get the hello quantum world, which is probably is too much for using quantum computers for just saying hello quantum world. But yeah, well, it's working. So this one is later in the next meetup we can talk about, for example, how to use the simulator, quantum simulator, and how to run the simulator to run a certain for example some kind of like simulation. Maybe we can play around with that. Okay, so for example, this one I take from an example. For example, this one how we generate random using quantum Q sharp instead of C sharp. So this is how the quantum computing language, this is the qubit. So sample quantum random number generator using the qubit, and then put the qubit to superposition. It has 50% chance of being 0 or 1, because it can be 0 and 1, it can be in the middle, it can be I don't know where. And then after that they can reset the qubit value to measure, and then this one is really mimicking the quantum computer, but actually using the classical computer. So if you using Q sharp, you will feel behind this is actually the quantum computer, but actually it's not. If for small thing it feels like no issue, but if probably later if you try to have some kind of like high simulation or using a lot of algorithm, then you can feel the PC is unable to deal with this kind of situation. The good thing is, while I'm running this, they have the other one, which is the Azure computer. Okay, the binder still here. So Azure quantum computing. So this one, if you want to do some more than just your PC, then you can do this Azure Quantum Preview. So you can play around using the same language, which is use QDK for the development kit and Qsharp for language. And you can play around with this, probably maybe using for real thing, but with not so many qubits in use. I don't know the because probably this one product preview. I don't know whether it has pricing, but I think this one is for preview and testing only. So okay, forget about the binder. It's not working. This one also launch attempt one failed trying. Let's try. Hey, it's working. Okay, Chrome is working. Okay, so this one, is Jupyter, right? So in here we have a lot of folders. So we just go to the samples. I just want to make it fast. And then maybe if you want to start, you go to getting started. And then you go to the intro to IQ Sharp. Okay, so you go here. And then you open the notebook, Jupyter notebook. Okay. So in here you can play around exactly like you use in Python, but it's actually Qsharp, which is quite amazing. This is the same thing. If you want to say hello, you just say hello. And then invalid, this one, if you want to see the error, you can see that actually they can show you the error. This one is another way to say hello. And then this is how to say to get the pi. Uh, just want to go all the way first. Before next meetup, we will going to go more deeply into this. Like for example, simulate this. You see this this notation is actually talking about the qubit spinning superposition, and later we can play around with this. Okay, so if we go back to my presentation, and I am going to switch back to the OBS here. Oop. Then the next one is the resource. So this is the resource that you can go is the marketplace to get the quantum development kit. You just install it in your Visual Studio or Visual Studio Code, and you just run. Or you can use Jupyter Notebook, spin a Docker, and then yes, you just use it to learn the quantum computing language. And then this is the example, the one that I showed to you just now, how to for solving simulation in the logistics in container terminal port, for example. That's the thing that you can learn for quantum computing. Uh, so I guess that's it for today. For my presentation, it's not much because this is my first meetup as well for quantum computing. Hopefully, the next meetup, hopefully we can do in-person meetup if everything goes very good in Singapore here. We going to do that, and then maybe before I do that, let me check if there is a question. Okay, we don't have questions. So I guess that's it for our meetup. And I would like to say again, thank you for the participants. And hopefully we can learn something. And next meetup, we're going to do coding using Qsharp. Uh, but probably maybe we will talk a little bit more about qubits and how we play around with the qubits. And we still have to learn about, for example, like there's a so-called entanglement, superposition. So this kind of jargon or term in quantum computing that I can share with you and we can learn together. Hopefully, there is some physicists joining this meetup that can help me because I want to learn this, but not too, I'm just saying, not too very deep because I just want to create a software using a quantum computer using Qsharp and then someday be able to be run in quantum computer. So that is in this meetup. So in that case, I would like to say thank you. You can send me questions to my Twitter here. And again, thank you very much and stay safe and have a good night.